The following interview was recorded on June 4th, 1995.
And we're talking with Ken Piletic,
otherwise known as W9ZMR. You want to hear the story about the interferometer and Sputnik 1 and all that neat stuff?
This is what I want to hear.
Okay. Let's start back in 1957, because that's when Sputnik 1 was launched in 1957. I was down at the University of Illinois. I've been playing with tape recorders for a long time, and I always have a tape recorder with me. And I was staying at Newman Hall. It's a Catholic residence hall, I guess you call it. And Newman Hall itself was full. They have like half a dozen annexes. So I was in one of these annexes, which was a house, and they divide up some of the rooms in the house, and there were 6 of us in this room. There were 3 double bunk beds in order that they could get some desks and a place to study and whatever. So anyway, there's one particular night, I'd already sacked out, and 2 of my roommates were out walking in the campus, and they happened to be down by the university's observatory. They had a big observatory down there, and this was pretty late at night. They come back, running out of breath, and they said, grab your tape recorder. They woke me up first. They said, grab your tape recorder and get down by the observatory.
Tell us a little bit about this portable tape recorder you had.
This tape recorder was a VM Model 700. VM is Voice of Music. And this thing, I guess it must have weighed at least 30 pounds. It was a 7.5 IPS or 3 3/4, a 2-speed, half-track mono. It runs 7-inch reel. That was the biggest reel you could get on it. A microphone input, and it also had a high-level input. Built-in amplifier. It had a 6x9 oval woofer and a little 3-inch tweeter.
Oh, no kidding.
Oh, yeah. It was a great sounding machine.
Ahead of its day, really.
Oh, yeah.
And were you kind of known on campus as that's the kid with the tape recorder?
Yes, that's basically it. Okay. So he says, grab your tape recorder and get over to the observatory. Well, why should I grab my tape recorder and get over to the observatory? Wake me up out of a sound sleep, this kind of thing. And they said, there's something going on, and these professors are all running around there, and the guy said, we need a tape recorder. And I said, my roommate has a tape recorder, and they said, get him over here with his tape recorder. So get over there with your tape recorder. So I said, okay, that's good enough for me. Now, where I was and where the observatory was is at opposite ends of the campus, at least a mile away. And this thing weighs, like I said, about 30 pounds. And my mode of transportation was by foot. So I had to carry this dumb thing. And, of course, a couple empty tapes. I had no idea why they needed this thing. But they told me something about a satellite. Figured observatory, they're talking about the moon. Because astronomers, they wouldn't say moon, they'd say satellite. And he says, no, it's an artificial satellite. In fact, that's what they called it. They didn't call it Sputnik 1. They call it the artificial satellite. I got over to the observatory, and I met this guy by the name of George Swenson. I had never been in the observatory before. In fact, I didn't even know where the observatory was. I had to ask somebody. And we went into the basement of the observatory. The first thing that struck me was there was no telescope down there. The telescope was up on top. You don't just set a telescope on the ground and look in it. What they do is they build a foundation for this thing. It's got to be 20 feet square, maybe bigger. Solid rock and concrete. And it goes way down into the earth. And then they build like a pyramid. It's like a truncated pyramid for you mathematicians out there. And then this thing goes up for 2 stories. The top of this thing is flat, and they mount the telescope on that. So the basement of the observatory basically was a foundation for the building, and in the center of this thing is this big concrete wall. And you walk all the way around the outside. And so if you want to go to any place, you can go either right or left, you'll get there, because it's a round building with this big block of concrete in the center. I think I visited the observatory for many, many days in a row before I actually saw the telescope. So I went down the basement there, and there is an old Hammerlin Super Pro. It's a general coverage receiver, and it covered from the low end of the broadcast band up to something like 50 megahertz. They called them megacycles back then. And they said, the Russians launched an artificial satellite, and we are trying to listen to it. It's sending down a radio signal. And this thing comes through on 2 frequencies, 20 megacycles and 40 megacycles. There's a lot of broadcast stations, foreign broadcasts, and all kinds of different things on 20 megacycles, and they knew they'd be hearing a lot of other things there than what they wanted to hear, but 40, there's like nothing there that we could hear. They opted for that, and somewhere along the line, they scrounged this Hammerlin Super Pro, which is a real good receiver for its day. It's all vacuum tubes, and they said, connect up your tape recorder to the output. We don't want a microphone on that, we want the tape recorder connected. So I connected it to this radio. Now we have to wait for the signal. So they explained to me what this thing was. The Russians launched this artificial satellite. They announced on Radio Moscow that they had launched this thing about an hour before. George Swenson calculated that it takes about 90 minutes for this thing to go around the Earth, an hour and a half. And what he's trying to do is copy a signal off of that thing. When it comes around, they got about 30 minutes to go. And he wants to hear this thing because we don't know how long the batteries are going to last. And now we're going to go outside and string some kind of an antenna and connect it to the radio. So we did this. They did this. I watched.
Did they have to wake up any other students?
Oh, there were all kinds of people there. They were mostly grad students. I was the only undergrad that was there at this time.
Because you had a tape recorder.
Because I had a tape recorder, that's right.
Yeah.
So I got to watch these guys put this aerial up. And now we all come back in and we're listening. And suddenly we hear this thing. And now what this thing was a carrier that went on and off. It was what they call a CW carrier, which means you're not going to hear it. You can watch it on the meter. It comes on and it goes off. Well, as most of us hams know, you turn a thing on your radio called a BFO. It's a beat frequency oscillator, and that generates a tone. So when it hears a carrier, you hear this tone come out. You have control over what this tone is going to be. You can control the pitch and you can control the amplitude. All this thing does is takes the signal that's turning on or off or whatever and adds a tone to it. So what we did is we didn't know what we were going to hear, so we turned the thing on and we heard something. We saw a carrier coming up on the S meter. That's a signal strength meter, and you can see this thing on and off, and you can hear the background noise go away as the signal gets stronger, and then the background noise comes back. So very quickly we realized you have to turn the BFO on and copy it like a CW signal. I turned on the tape recorder and we recorded a pass of this thing. Now this guy that I've been telling you about, George Swenson, is a radio astronomer by trade. He is a professor, PhD type. You can look him up in the you can look him up in anything. He is the world authority on radio astronomy. He is in the Encyclopedia Britannica. He's well recognized in the astronomy community. Anyway, what these guys had planned to do, they had been working on this for quite a while with the U.S. artificial satellite that we were supposed to launch in about 2 years. Our stuff was going to run on 108 megahertz, right at the high end of the broadcast band for FM. That's where all our telemetering stuff was going to take place. So when they hear the signal going beep, 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 they got a couple of decisions to make. They were set up for Doppler, where they could tune this thing in with a Doppler shift, which would be a difference in the pitch. It would go like beep, 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 beep. That's a Doppler. That's when it's going away from you. When it's coming towards you, it goes beep, 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 beep. And you can take the difference in the pitch, and from that you can calculate a lot of things. If it was a steady carrier, that probably would have been the way that they did it. When they realized it was an intermittent carrier, they figured that there was a better way to do it, and that was with a thing called an interferometer. They said, we got 90 minutes to set up an interferometer. What an interferometer is basically an electronic snow fence. It's like a picket fence that they put up alongside of the road in the wintertime. When the wind blows through this thing, it blows through the pickets, and the wind kind of crosses itself. It comes from the right and the left, and when they hit, they cancel each other out. And if there's snow in the wind, it piles up the snow right there rather than getting it on the road. And they put these things along the highway. Well, an interferometer does the same thing electronically. There is a point where those signals are going to cancel each other out. The net result is if you have two antennas that are tuned to the same frequency, in this case 40 megahertz, one at one end of the yard, one at the other end of the yard, and you connect them up to a common feed line, and you know how long that feed line is, and connect that feed line to your radio, you will hear a signal that will get stronger and weaker as this signal changes position. The satellite is going to fly over, and as it flies over, it's going to give you reinforcement and cancellation of the RF signal that comes from the antenna. So what's going to happen is you're going to hear a louder signal and then a weaker signal, and then a louder signal and a weaker signal. And Swenson figured this out. He said, we'll put up an interferometer, and as the thing goes by, you'll be able to see on the S meter that it's going to get stronger and weaker, and it's going to come up to a point. Every beep is going to be a different signal strength than the previous beep and the following beep. And they're going to either get stronger and stronger and stronger and stronger, and then they're going to get weaker and weaker and weaker and weaker as they go away. If we connect a graphic ammeter, it's a meter with ink on the end of it, and it draws with an ink mark as the meter moves. You have a roll of paper, and the paper moves at a known rate, and this graphic ammeter swings back and forth. It will draw a pattern. Every time it beeps, it'll swing to the right. When it stops beeping, it'll swing to the left. And then you can see on the picture that this thing draws, the envelope of this will have high points and low points. And then, with a ruler, you can measure the distance between the peaks and the valleys. And if you know how far apart these are, time-wise, in addition to distance-wise, then you can calculate all kinds of things. So what he did was, he says, we'll record the beeps on the graphic ammeter. Get another receiver over here. We'll get WWV. That's the National Bureau of Standards time signal. And you hear this little click every second. And that is very, very, very accurate. So what we'll do is we'll listen to this other receiver, and we'll put a little mark on this piece of paper every second as it goes across. And now we'll know how far apart these things are time-wise. And we'll be able to count the seconds from the highest peak to the next highest peak. We know how many seconds it takes. We can figure out a lot of things about the satellite. We can tell how fast it's moving, when it'll be back again, We can tell relatively the signal strength of this thing. We can tell how much it weighs. We can tell how big a rocket it took to get it up there. We can tell everything except how long the batteries are going to last, because we don't know what kind of batteries they use. But anything there is to know about this, we are going to be able to figure that out from these little beeps that come down. So George is down there with all his grad students, and I'm there with my tape recorder. And my second job, he gave me a second job, was to listen on the other radio and with a ballpoint pen to make marks on this paper as it came out every second. So now I got a thing on the meter where I know exactly where I'm going to draw the line relative to the meter, so these things are going to be equally spaced. Tick, tick. And every time WWV goes, I take my little ballpoint pen and I put a mark on this paper. So we get all this. It starts coming now. Here it comes. You can hear it very, very faintly in the background. Pretty soon it gets real strong, and the pass lasted about 10 minutes. About the same as our Oscars do today. It mathematics out that these things are going to be about 10 minutes in duration. Because if you figure that the size of the Earth and all that, that's how long it takes to go around when you launch them in that particular orbit. So here comes the thing, and mostly because of where Russia is, they have a pretty high inclined orbit. Depending on how far away from the equator you are when you launch, and usually you launch towards the east to get the spin of the Earth to help you with your launch. If you, say for example, launch right on the equator and you launch pointing due east, you will get a 0 degree, because you're right on the equator. If you're at 40 degrees latitude and you launch pointing due east, you will be a 40 degree inclination to the equator. And the further north you are, the more inclination you get if you launch due east. And you want to launch due east because that's when you get the maximum rotation of the Earth helping you launch. So I didn't know any of this. I learned all this in this Sputnik thing. But that's why they had to orient their antennas the particular way. The antennas were basically oriented north and south so that the direction of travel would be broadside to that, which would be east and west. We didn't know how long it was going to be up there. Well, as it turns out, it was up there for weeks and weeks and weeks. We had no idea the batteries would last that long. We figured maybe 2 or 3 passes and that would be it. The batteries would be dead. So anyway, this thing came around. They got a good pass. They read all this stuff off the thing and they calculated out everything there is to know. George made some kind of a telephone call, and he told whoever he told what they found. He gets a telephone call back, and they said, "You're wrong." They said, "Everybody else, all the other tracking stations," you got to remember, these were tracking stations that were originally set up for the United States stuff, and there was one at the University of Illinois. All the other universities and various observatories around the world were all tracking this thing. They all had some kind of a headquarters where all this data is filtering in. And he says, "George, you're wrong. You're not lining up with anybody else. Everybody says something different, but you don't agree with any of them." Well, George says, "No problem. It'll be back in 90 minutes from when we took this data. We'll verify it if we hear it." So here it comes around again. We copy it again. We go through the same old routine again. Paper comes out the same as it did before. These guys have got paper now all over the floor of the observatory. They do all of this, and they get the exact same results. So George makes another phone call, and he says, "Sorry, guys, we came out exactly the same as we did the first time, and we don't see where we're doing anything wrong." And now, by this time now, this has been going on, and they launched this thing at night. It's getting bright outside now. It's getting into daylight hours. None of these guys have had any sleep. So here's another one that says, "Well, George, your data is the same, but everybody else's data is different from what they had the first time." Well, there'll be another pass in 90 minutes. If we can hear it, we'll do it again. So 90 minutes later, they do the same thing, and while they're making the calculations, the telephone rings. It was Western Union. And then they came over and they brought the telegram. It said something like, "Congratulations, you're the only one in the United States with accurate data." Everybody else with all their fancy equipment was coming out wrong, and George with his little Australian Angus graphic ammeter and a couple of wires out in the yard for an aerial, which he made into an interferometer, and a Hammerland Super Pro.
And you and your pen
and
marking
my
the
pen
graph?
marking this thing.
Oh, yeah.
That was the beginning of it.